In this video, we're going to look at Riemann's definition for the definite integral. But before looking at the definition, I want to actually remember what we already know about definite integrals. First of all, we have the basic definition, which is that the definite integral from a to b of f of x dx is the signed area trapped by y is equal to f of x, the x-axis, and over the interval between a and b. We also know the second fundamental theorem of calculus, which states that if f of x is a continuous function defined on a closed interval from a to b, and capital F is any antiderivative of little f, then the definite integral from a to b of f of x dx is nothing more than capital F of b minus capital F of a. In other words, it's important to realize that the fundamental theorem gives us a super easy way of evaluating definite integrals whenever we are lucky enough to have an antiderivative for the integrand. And as a basic example, consider this particular definite integral. The definite integral from 1 to 5 of x squared dx, well, x squared has an easy antiderivative. It's x cubed over 3, and we simply evaluate that at 5. We evaluate it at 1. We stick a minus sign in between those two numbers, and we're done. We've known this now for a while, but there is also something that we need to keep in mind. There is a fundamental problem with the fundamental theorem. I want you to consider this integral here. The integral from 0 to 1 of the sine of e raised to the x squared. And this particular integral equals signed area underneath the shaded plot generated by this Mathematica input cell. And I want to notice that in this particular plot, we clearly have a chunk of area, and that chunk of area is going to be given by 0 to 1, the integral between 0 and 1 of sine of e to the x squared dx. But if I try and find an antiderivative of this particular integrand for any using the techniques that we know, there is no easy antiderivative. And yet, if I start thinking about this chunk of area, I can easily put a line at y is equal to 1 and another line at x is equal to 1, and I've got a box here now that has area 1, and the area of this particular curve under the curve is certainly less than that box. So this integral is certainly less than 1. And so we'd like to be able to find that area. It looks like a nice number. Well, we can ask Mathematica if Mathematica knows. So we'll use Mathematica's integrate command. Unfortunately, let's look at the answer. What Mathematica spits right back out at us is the integral between 0 and 1 of the sine of e to the x squared. In other words, Mathematica doesn't have an antiderivative for this function either. And that brings up an important observation. If we or Mathematica cannot find an antiderivative for f of x, we can't use the fundamental theorem to evaluate the definite integral, even if we can see the area. So what does this mean? Well, Bernard Riemann had an idea for finding areas when we can't find an antiderivative, and we're going to follow Riemann's lead. The first thing that Riemann decided to do was that we can hopefully estimate the area underneath the curve in some kind of a systematic function, and then we can work on coming up with a way to see whether or not we can make our estimate get better and better and better. Now, his systematic way of estimating the area was to use rectangles. The first thing he did is he said, we're going to slice the interval between a and b into a certain number of equal width subintervals. So here I've got the first subinterval, the second one, the third one, the fourth one, and the fifth one. And I'm going to refer to these as slices. So we slice this thing into 5 equal slices. And what we're going to do is we're going to put a rectangle on each slice. And we're going to do this by choosing a point on the curve inside the slice to determine the height of the rectangle. Well, let's see how that looks. On our 5 slices, here are 5 random rectangles. And these orange dots, and let's see if I can make this picture bigger to make those dots a little bit easier to see. These orange dots are points on the curve that are being used to determine the height of the appropriate rectangle. So this first dot, the y-coordinate of it, determines the height of the first rectangle. The y-coordinate of this point determines the height of the second rectangle. The y-coordinate of this third pink dot determines the height of the third rectangle. This fourth dot determines the height of the fourth rectangle, and this fifth pink dot determines the height of the fifth rectangle. Now these are random rectangles, so if I reactivate the command, I get a different set of rectangles. And if I do it again, I get a different set of rectangles. And you can do this all day long. Now, the idea that there's another idea that I should point out, which is that sometimes systematic ways of picking the rectangles, such as always picking the right endpoint, or always picking the left endpoint, or always picking the midpoint of the interval for drawing the height of the rectangle, these ways of looking at finding the rectangles have their advantages, and you explored those advantages in Lab 2, which was done last week. Well, what I want to notice is just like we noticed last week, Riemann observed that the more rectangles, no matter which type you have, the better the estimate. So let's look at what happens when we let the number of left rectangles grow large. There's our 10 left rectangle estimate. Here's our 100 left rectangle estimate. And this area is clearly a much better match for the area than that one. And at 1,000 left rectangles, visually we cannot distinguish between 1,000 left rectangles and the actual area. And the estimate has now settled down to 0.886 something or other. Well, what happens when we let the number of right rectangles grow? There's our 10 right rectangle estimate, our 100 right rectangle estimate, and our 1,000 right rectangle estimate. And by the time we pile in 1,000 right rectangles, we can't tell the area of the rectangles apart from the area under the curve. And again, notice that it has settled down to about 0.886. Well, if we look at the number of middle rectangles and let them grow, there's the 10 middle rectangle estimate. Here's the 100 middle rectangle estimate. And here's the 1,000 middle rectangle estimate. And by the time we got 1,000 middle rectangles, we can't tell the rectangles apart from the area, and the estimate has settled down to about 0.886 again. And it turns out that it doesn't matter what kind of rectangles. If we look at random rectangles, there's a random 10 random rectangle estimate. Here is a 100 random rectangle estimate. But by the time I pick 1,000 random rectangles, it's hard to tell the random rectangle estimate apart from the area underneath the curve. And again, you'll notice that with 1,000 random rectangles, my estimate is settled down to about 0.886. So we've got compelling evidence that the true value of our integral that we are looking at, it's got to be somewhere around 0.886. But we don't really know exactly what it is yet. So let's continue looking at Riemann's ideas. Now, Riemann had this brilliant idea. He thought that if you he thought that if you let the number of rectangles get bigger and bigger and bigger, and their widths would have to go to 0, that the area is then going to become that limit. And So what this is saying is that the true exact area is going to be the limit as the number of rectangles gets big and the width of the rectangles goes to 0 of the sum of the areas of the rectangles. That was what Riemann's insight was. Now, like I said, n is the number of rectangles and delta x is the width of each rectangle. Now, to translate this thing up here into more symbols, we can rewrite that equation there as this equation. All I've done is I've let RK be the area of rectangle K. So now our true area is the limit as n gets big and delta x goes to 0 of the sum R1 plus R2 plus ... all the way down to Rn. Now, Riemann also knew this. The area of rectangle K can be thought of as the height times the width. And the height of a rectangle is going to be the y-coordinate of a point on the curve that is inside slice K. So the height of my rectangle K is going to be given by f of ck, where ck is some x value chosen randomly from the kth slice. And because we are chopping the interval into n equal width sub-intervals, in other words, n slices that all have the same width, the width of my rectangle can be given by delta x, which is the total width of the interval that we are integrating over, divided by the number of slices. And that's going to be b minus a divided by n. And that is because all the slices have the same width. So, the area of rectangle K is going to be the height times the width, which is going to be f of ck times delta x, where ck is any x value from the kth slice, and delta x is just given by b minus a over n. And that means Riemann's actual definition for the area under a curve, even non-continuous ones, can be written this way. The area is going to be the limit as n gets big and delta x shrinks to 0 of the sum of the areas of the rectangles. But what that means is that the area is going to be the limit as the number of rectangles grows and the width shrinks to 0 of R1 plus R2 plus R3 plus all the way up to plus Rn, where Rk is nothing more than the area of rectangle K. And that means our area can be written symbolically as the limit as the number of rectangles gets big and their widths go to 0. So let me state this pretty clearly. The area is going to be the limit as the number of rectangles gets big and their width shrinks to 0 of the sum of the areas of the rectangles. And f of c1 times delta x is going to be the area of the first rectangle. F of c2 times delta x is going to be the area of the second rectangle. And we keep going until we get to the area of the last rectangle, which is f of cn times delta x. And that's what this particular shaded in formula actually means. And the net result of this is that we have the final formal definition of a definite integral, and it looks like this. The formal definition of the definite integral is the integral, let's see, I got to highlight that again. The integral of f of x from a to b is going to be given by the limit as the number of rectangles goes to infinity and their width shrinks to 0 of the areas of the rectangles all added together. And f of c1 times delta x is the area of rectangle 1. F of c2 times delta x is the area of rectangle 2. And we keep going until we get all the way up to f of cn times delta x is the area of rectangle n. So ck is any x value chosen from the kth slight, and delta x is b minus a over n. And the final thing that I want to make a note of here is that f of ck is the height of rectangle k, and delta x is the width of delta x of the kth rectangle. And so that's why this is the sum of the areas of the rectangles. In the next set of videos and in the rest of this learning module, we're going to continue looking at this definition of the definite integral, and we're going to learn how to actually work with it.